Welcome back. So we'll continue with our discussion on spin system nomenclature. That is what is called well-known Popper nomenclature. Remember, in the last class, we discussed a simple two spins which are weakly coupled, which are identified as A and X. AX spin system in the NMR jargon, in the Popper nomenclature, are weakly coupled because remember I have been telling you that A and X are far away separate in the alphabet order. When that means the chemical separation between them is quite large compared to the J coupling between them. As a consequence, such systems are weakly coupled. The weakly coupled are represented like this. The two spin example for AX, which is weakly coupled, we worked out and we saw that chemical shoots are far away separated, and we know the two states. We calculated even what is the eigenvalues of these each of these spin state, found out the frequency separations, and we got each spin is split into a doublet, and whose frequency separations correspond to coupling between them called JAX, and a center of each doublet gives you corresponding chemical list of the two protons. And also I said in the weakly coupled case, the intensity ratio is 1:1:1. All the four peaks of this AX spin system are weakly coupled. This is an important point which you must remember when you want to analyze two weakly coupled spin system. I took the example of homonuclear spin. There is no reason why it should be homonuclear. You can also take heteronuclear also. Heteronuclear weakly coupled is also possible, right? That's what we discussed long back. Now I want to give you one general formula. You must remember this formula because always it is very useful in understanding and analyzing the NMR spectrum. Logically, I wanted to tell you when we have two coupled spin systems, we got four peaks. Okay, when we have one spin system, we got one peak. And remember, when we were analyzing calculating the number of possible transitions in three coupled spin system, I said we are going to get 12 peaks. Remember, we observed 12 peaks in AMX spin system. Remember, in one of the classes, we found out all the possible energy levels, and we have got 4 transitions for A, 4 for M, and 4 for X. And also we got combination transitions for 3. Totally we got 15 transitions. Now logic. One spin gives 1 line, 2 spin give 4 lines, and 3 spins can give 15 lines. How many 4 will give? If 5 coupled spins are there, how many lines it can give? We can extend the logic like this. So I'll give you a general formula now. Please remember, if there are n coupled spins, if there are n coupled spins, there will be total of 2n C n minus 1 transitions. Very important to remember. If I have n coupled spins, there will be total of 2n C n minus 1 transitions. That is, I consider the example of 3 spins. 3 spin, 3 into 2, 6. N minus 1, 2. 6C2, it is a combination. Work it out. Very simple. 6 factorial over 4 factorial into 2 factorial. Then it is going to be 15. So 3 coupled spin system can give maximum of 15 transitions. That's what we observed. For AMX spin, remember, 12 transitions plus 3 combinations, totally 15 we observed. That's okay. Now, let us go to the complicated spin system. If there are 4 spins coupled, let us say 4 protons are coupled, how many peaks I must get? Remember, it is same 2n Cn minus 1 formula. You plug it in, n is 4 here, 2 into 4 it is 8, n minus 1 it is 4 minus 1, 3, 8C3. It is 8 factorial over 3 factorial into 5 factorial. So 8 into 7 into 6 divided by 6. So 8 into 7, it is 56. So 4 coupled spins will give you 56 transitions. It is amazing. You go to even higher coupled spin system. For example, if you go to simple 7-spin systems, believe me, you are going to get nearly 3000 transitions. 6 spins can give you 792 transitions. Like that, if you keep on adding one spin, the number of transitions keeps on increasing drastically. But the question comes, do all these peaks are necessary to analyze the spectrum and get the coupling information or chemical shift information? That's all you should get from the analysis of the spectrum. Okay, if I analyze the spectrum, I get chemical shifts and coupling constant after making peak assignments. Go back to the simple 2-spin case. You got 4 peaks, 2 AX spin system coupled, and you got 4 peaks. I get chemical shift at the center of this doublet. I get chemical shift at the center of this doublet. This doublet separation gives me J coupling. This doublet separation also gives me J coupling. That means this information is redundant. I can get only from one of the doublet. I don't need to have other doublet, right? I don't need to analyze this one to get the J coupling. It means, remember, this is for a simple 2-spin. If you go to 3-spin, I can show you sometimes or most of the time, the information content is highly redundant. You don't need all the transitions to analyze and get the required spectral information. Okay, please remember, most of these transitions are highly redundant and only few of them are sufficient to get chemical shifts and J couplings. Now, let us go by, I'll give you a simple this thing. What are the things, information which you require? A general formula. If I have n coupled spin systems, what information you will get? If all are chemically inequivalent, you will get n chemical shifts. You must get n chemical shifts from the spectrum. If there are n coupled spin systems which are chemically inequivalent, analyze each group for different chemical shifts, you must get chemical shift information. So n coupled spin system should give you n chemical shifts. And how many couplings you get? There is a formula for it. It is always given by n into n minus 1 by 2. You understand? N into n minus 1 by 2. Well, let us take the example for 3-spin case. N is 3. 3 into n minus 1. That is 3 into 2 by 2. If there are 3 coupled spin system, maximum you can get 3 coupling information. You have to get only 3, not more than that. How? Understand, 3 spins are coupled 1, 2 and 3. There can be coupling between 1 and 2, 1 and 3 and 2 and 3. That's all. There is no need to worry about any other thing. Similar, that's why. So remember the formula. If you have n coupled spin system, this analysis of the spectrum will give you n chemical shifts and n into n minus 1 by 2 couplings. And how many peaks will we get in the spectrum? It is given by 2nc n minus 1. These are the 3 important formula, you remember. Okay. Now with this, we'll take a simple example of a homonuclear AX spin system. This is a third-fin molecule. I even showed this earlier also. What is the chemical shift separation between these? The frequency is given here, already expressed in here. It is in ppm. It has been converted to frequency at some spectrometer. No problem. This is A. Which is A? Which is X? My freedom. I can choose this A or this X. Doesn't matter. Now, what is the chemical shift separation between these two? Find out. It is close to 3830350, 300 hertz. Approximately, chemical shift separation is 300 hertz between this and this. And the coupling is what between these two? Only 5.77. Now, plug in this 300 as a difference value of chemical shift, divided by J coupling. You know what you are going to get? The ratio is 50.8. What did I say? Conditions for weakly coupled. The chemical shift difference divided by J coupling should be sufficiently large at least it should be equal to or greater than 50. So now it is of that order. And it must be weakly coupled AX-pen system. A realistic molecule I'm giving you. So what information you can get by analyzing this? Go to the center of this doublet. It gives you chemical shift of A, if this is A. Go to center of this doublet, gives you chemical shift of X. Measure this doublet separation, you get J coupling. That's all. All the three information you can get in just less than a minute by analysis of the spectrum. What did I say about the intensities of weakly coupled AX spin? All are equal intensity, like all should be 1:1:1 intensity. Okay, this is what it is. And this is a realistic situation like another molecule. A molecule here consider proton A and proton X. And this is identified as X, this is A. Doesn't matter how we do is our way of identifying. I could make this as A and this X also. This is the doublet corresponding to one of the coupled spins of AX spin system. This is the other doublet. Now what information you will get? Center of this will give you chemical shift of X. Center of this will give you chemical shift of A. This separation will give you JAX. But notice one small thing here. What did I say about the intensity? I said the intensities have to be equal, right? Look at this intensity. Are they equal? These intensities are not equal. What does it mean? I said the weakly coupled case, there must be of equal intensity. There is a what we call as the roof effect. It appears the peak is moving like this, and this is called a roof effect. And that's when you go to the strongly coupled, I'll give you an example that tells me these two coupled spins are not 100% weakly coupled. If they're 100% weakly coupled, then all the four peaks should be of equal intensity. This type of tilting in a particular direction, these two, one moves towards tilts to the right, one tilts to the left. This roof effect will not be there. That shows it is not 100% AX coupled. There is a residual strong coupling effect is still there. Partial, AB character is also present here. Partial AB character. It is not 100% AX. Now, the question is, if I have to make it 100% AX spin system with all of equal intensity, what we will do? What I have to do without doing anything? Without doing anything for the sample, I want to make it AX spin system. I told you, remember, the chemical shift separation, I have to enhance it so that the ratio of delta by J becomes much larger than 50. What do? Simply record the sample, take the sample, go to higher magnetic field. Supposing this is done at 400, you go and then start recording the spectrum at 800 megahertz. Then what will happen is this roof effect will disappear. Strong coupling character, minute strong coupling character which is present here will disappear. You will get 4 peaks of equal intensity. This is what I wanted to tell you. Please remember, if the system is strongly coupled and appears weakly coupled, but with a minute strong coupling character is present, simply go to little bit higher magnetic field and see whether this pattern disappears and get peaks of equal intensity. Okay, this is a hypothetical example of a AX spin system, heteronuclear case. What happens here? A is proton, X is fluorine. It has to be a heteronuclear. Remember, I have been telling you, heteronuclear case is always weakly coupled because this chemical shift and this chemical shift is megahertz away. The resonating frequency for this at 500 megahertz. If it is 500, fluorine comes at 470, so about 30 megahertz away, and this coupling is very small. So heteronuclear has to be weakly coupled. Look at this. I mean, you cannot get both the peaks in one spectrum. I'll give a break here. This is in the proton resonance, I'll get this proton peak. In the fluorine resonance, I'll get this doublet. So what do you get? Center of this will give me proton chemical shift. Center of this will give me fluorine chemical shift. This separation will give me J coupling between proton and fluorine. Same way you get this J coupling information, you can also get from proton spectrum. Don't think that I got both fluorine and proton spectrum in one this thing. There should be a break in this. This is in the proton resonance. This is in the fluorine resonance. It is not in the same single spectrum. Okay. So if I give the break here like this, then you will understand. I should clearly write this is a proton resonance. This is a fluorine resonance. Two different spectra. They are not same spectrum. Okay. So with this, and also you notice here, because the perfectly weakly coupled spin system, the intensities are exactly equal. 1:1:1. This is what I was telling you. We should see in the realistic example of homonuclear. You are not getting that. You are getting roof effect. That should not come. So now this is a real perfect example of a weakly coupled AX spin system. Now we'll go a little bit further. I will look at two spin strongly coupled case. What is strongly coupled case? This I have to represent by a letter very close in the alphabet order. Earlier it was A and X was far away. Now I am going to take letter next to A, that is AB. I consider JAB. So this is proton A and proton B. And what are the possibilities you can think of? In this AB case, remember chemical shift of A and B are not same. If they are same, it is different. They are equivalent nuclei. Okay, or magnetically or chemically equivalent, no problem. But now in this case, chemical shift has to be different. And delta chemical shift separation, unlike AX spin, it is not very large. It is small, very small, comparable to JAB. Remember, it is comparable to JAB. And JAB is not zero. If JAB is zero, if you don't see the coupling, then it's a different case. But remember, JAB is not zero. Chemical shift separation is comparable to coupling constant, and they are not, chemical shifts are not same. This is a condition for AB case strongly coupled. And heteronuclear AB, what happens? It is impossible. I said heteronuclear couplings, heteronuclear coupled spins are always weakly coupled because the chemical shifts are megahertz away compared to couplings of few hertz. So heteronuclear case, strong coupling is impossible. Always they are weakly coupled. Okay. When the spins are strongly coupled, we say spectra are second order. When the spins are weakly coupled, the spectra are first order. What is the difference between first order spectrum and second order spectrum? I told you several times, first order spectrum is easily analyzable, like AX example. Get the chemical shift here and measure the separation to get J coupling. That is simple first order analysis. Straightforward analysis to get the information is a first order analysis without getting into theoretical calculations or computation. In the strongly coupled case, intensities of lines do not follow the normal rules. Unlike weakly coupled, all are equal intensity. In a strongly coupled two spin case, intensities are not, all are not equal. That is another. We saw that, in a minute AB character was present in the AX case, we saw roof effect. Intensities are not same. I said there is a minute strong coupling character there. This is what happened. When there is a strong coupling effect, intensities do not follow normal rules. You don't get lines of equal intensity. And sometimes it may so happen, instead of normally expected lines, you get more lines. How is it possible? You may ask me a question. How can we expect more lines than what is possible? It is possible. I'll give you an example when we go further. You please remember, in AMX spin system, what did we do? We got 4 transitions for A, 4 for M, and 4 for X. But also I showed you there are 3 combination transitions where all the 3 spins will flip at a time, still retaining the change in the total magnetic quantum number of energies, these 2 energy states, still as +1 or -1, it retains that. But still 3 spins can change at this time, alpha to beta, beta to alpha. That is called combination transitions. Such transitions are not seen in weakly coupled, but they are seen in strongly coupled case. Understand the point? That is why In strongly coupled spin system, sometimes you get extra peaks, more peaks than what is expected in the weakly coupled spin system. This is the spectrum of AB, AB spin, where A and B are strongly coupled. Look at this one. Are they having equal intensity? No. This is a clear indication AB. And also the roof effect. Look at it. This is going like this. This is going like this. This is called roof effect. Remember, in the AB coupled case, intensities of the central two lines are equal. Intensities of the outer two lines are equal. I2 is equal to I3. Intensity of I second peak and third peak is same. Intensity of first and the fourth are same. This is a pattern we expect for AB. Okay, always remember, if you observe a spectrum like this in your molecule where chemical sheet separation is small, it is strongly coupled. In which case, you don't get the chemical shift just by making the center of this. I'll go and take the center and measure the chemical shift. No, it's not possible. So there is a different way of getting chemical shifts there in case. Okay, in strongly coupled case, you don't get individual chemical shifts. I can only give you difference of chemical shifts. You understand? In the weakly coupled case, I know chemical shift of A, I know chemical shift of X very precisely. But in the strongly coupled case, AB, I do not know chemical shift of A, I do not know chemical shift of B. But I know the difference between A and B. The difference can be 10 hertz. Or if it is 10 hertz, one can be 15, other can be 5. One can be 30, other can be 20. Doesn't matter. The difference can always be said, but not individual chemical shifts in strongly coupled spin system. Now, this is how you get the difference of the chemical shifts. Simple formula. Outer lines I have mentioned as frequencies nu1 and nu4 here. Central two lines are nu2 and nu3 in the same order. Take nu1 minus nu4 difference, multiply by nu2 minus nu3 and take the square root of that. That gives you difference of chemical shift. Remember this formula. It is very, very useful to analyze. Don't forget that this should be in your fingertip. In a strongly coupled case, difference of the chemical shift between 1 and 4. Take the difference, multiply by the difference in the chemical shift of 2 and 3 and take the square root of it. That gives you delta delta or delta nu, frequency separation of two spins. I do not know the chemical shifts individually, but I know the difference. You understand? Now I can also get the JAB. JAB is very easy. You can just take the difference of these. Outer two lines here or outer two lines here. But not this one. Only outer two lines of the AB pattern gives you J. Alternately, there is a simple formula. Take nu1 minus nu2 plus nu3 minus nu4 divided by 2. It amounts to same. Instead of taking this, you take this and divide by 2. Instead of that, you measure only one of them. That's enough. This gives you J coupling. You don't have to use this formula. Take the frequencies, measure the frequency separation between outer lines, any two outer lines. This line or this line. That gives you J coupling. Remember this point in the AB spectrum, how to analyze. This is a complete analysis of the spectrum. Though simple, it's only two coupled spin system, is not possible without using quantum mechanics. You have to do quantum mechanical analysis. But I am not going to the detail. I am just giving you the information. This is enough if you know. Don't worry about how we get this. Remember, you take nu1 minus nu4, multiply by nu2 minus nu3, take the square root of that, you get chemical shift difference. Just measure the outer line separations of any of these doublet, this doublet and this doublet. You get J. That's all analysis of AB. So AB system gives centrosymmetric four lines. Remember, this is centrosymmetric four lines. It is symmetric with respect to center. Okay, and all peaks are not of equal intensity. Central peaks of identical intensity. To outer lines are of identical intensity. Whatever may be the coupling strength, regardless of whatever the coupling comes, whatever the strength of coupling, outer lines always gives you J coupling. Remember this one. You may not know this one. This you have to precisely calculate. Whereas the outer lines is very simple. Measure the frequency separation outer line. Whatever may be the pattern you get, you will get J coupling. That's very important information. You remember. Okay. On sign of the coupling again do not influence the spectral pattern. That we knew even in the weakly coupled case. So now you can also get the ratio of intensities very easily. You can find out the ratio. What is this? I know nu1, nu2, nu3, nu4. I know what are intensities. I called it as I1, I2, I3, I4. If I take I2 by I1 or I3 by I4, if I take this intensity is given by I1, I2 by I1 is nu4 by nu1 divided by nu2 minus nu3. Either of them. This is the formula you have to use. Take the separation of this and take the separation of this. Divide this separation by this separation, that will give you intensity. You understand? Now this separation becomes larger and larger. What will happen? Consider an example. Now nu1 minus nu4 becomes larger. This one peak comes here, one peak comes here. This becomes larger. Then what happens? This numerator becomes larger, denominator becomes smaller and smaller. The intensity ratio becomes larger and larger. That means this is more intensity, this becomes less intense. To understand the point, please, it is simple arithmetic I am showing you. In a strongly coupled case, you will get a spectrum like this. Take the ratio of the outer peak separation, ratio of the internal two peak separation, and then take this ratio. Chemical frequency separation here and between these two, and take the ratio that will give you intensity ratio of the peak. When this separation becomes larger and larger, then what happens? The intensity ratio becomes larger and larger, means outer lines become more and more intense, and this line, internal lines become more and more intense, outer lines become lesser and lesser intense. This is what happens. So, what does it tell you? Depending on the spectrum, depending on the chemical shift, depending on the separation or J coupling, your spectral intensity pattern drastically changes. Don't forget this. Depending upon the pattern, depending upon the spectral information like J coupling strength and chemical shift separation, your spectral pattern changes, intensity pattern changes drastically. That is a very, very important thing. Now I'll consider a situation. J coupling is very, 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 very small. What does it mean? I said in the strongly coupled case, outer line separation gives you J. It means this becomes very small. Let us say this peak comes here and this peak comes here because J is small. Then what should be the intensity pattern? Look at this one. Nu1 minus nu4 remains nu2 minus nu3 becomes very small. This intensity ratio becomes very large. So I2 will be large intensity compared to I1. Then what will happen? You get a spectrum like this. Okay. You get this will happen. If I keep on increasing, let us say J coupling becomes much, much smaller. Then it will become like this. Too close by, very high intense, and outside lines are like this. So what happens? As the coupling strength decreases, outer lines become smaller and smaller intensity, and internal lines become larger and larger intensity. Another interesting thing happens. This separation keeps on coming down. That also happens. Separation between the internal peaks keeps coming down. And this separation between internal peak and outer peaks keeps on increasing. Very interesting phenomenon. So don't have to worry too much. Simply look at this equation. Do some rough calculation. Keep on varying this frequency separation between this and this, and see what is going to happen. Nu2 minus nu3, if I find out, you keep on reducing this value and keep on increasing this value. Play around and see how the intensity changes here. This is a very interesting phenomena you are going to observe, and this pattern completely will be different when you change J or when you change the chemical shift separation. Let us see that now. This is a classic example of 2,4 dibromothiophene It is a strongly coupled AB spin system. Look at this pattern. What is happening? Here is the roof effect. That clearly indicates it is a strongly coupled spin system. So now I am giving you the frequencies here. When I give you the frequencies, you know what is J coupling. What is J coupling? It is the frequency between any two outer lines, I said. Now take this separation of these two. 7.52, forget about first two digits. 7.52 or 5.9, take it 6. It's close to 1.6 at J coupling. I think something is 6 minus, so 1.5. It is something is wrong written here. Anyway, outer lines has to be J. Some calculation mistake is there. Don't worry. Now chemical sheet separation. You find out what is JAB. It is frequency of the first line to fourth line divided by this one. You know that one. I have already discussed how to get the chemical sheet. This separation multiply by this separation into square root of that gives you chemical sheet separation. So now you find out what is ratio of chemical sheet separation by J coupling. This is much smaller. This tells you it is a strongly coupled system. Okay. Now this one. This is again 100 megahertz if I go. What happens? Look at this one. This is a different this thing. It is, let us say this is 1, 2, 3, 4. This is 3 and 5 dibromo. In this case, it is 4 and 5 dibromo. This is also AB spin system. Look at this roof pattern. You can see it is a perfect AB spin system. Now you can measure this separation gauge, you can get J, get this separation and get this separation, multiply, take the square root of this, you are going to get JAB. Okay. AB spin system has two limiting cases. When this becomes larger and larger chemical sheet separation compared to J coupling, you can take AB to AX. That's what you can do. I told you I have a strongly coupled spin system. Increase the magnetic field quite a bit, then this becomes larger. So you can make it AX. That's one limiting case. Alternately, you can keep on reducing such that so small, and after some time make sure that delta Ij is 0. There is no chemical sheet difference at all. They're equivalent spin, they overlap. It's like A2 spin system, like CH2 group. Both are equivalent protons. There is no coupling between them is seen. Then that is a situation where you are going to get A2 spin system. So AB can be taken by increasing the magnetic field enormously to AX spin system, or by in so happen if the chemical sheet separation, if it is made to be 0 and if the coupling between them are not reflected in the spectrum, it can become A2. So these are the limiting conditions of AB. So in the limiting conditions of AB, when chemical sheet become 0, two internal lines overlap, coalesce, completely overlap. Two internal lines overlap and you get a single peak, and outer lines completely disappear. That is a very interesting point. Remember, outer lines will completely disappear. This is standard example for an A2. A2, how many lines you get? Simple example, I gave you hydrogen atom. I'm sorry, hydrogen molecule. You take hydrogen molecule. There are two protons. They are chemically equivalent. No J coupling is seen. How many lines you expect? Only one peak. Classic example of A2 is hydrogen molecule. So one line, how do one line come? In principle, when two protons are coupled, you must get 4 lines. I said easily you can calculate 2nC n minus 1. How many lines you get? For 2, you can write down the formula 2nC n minus 1. So what is 2n? You have 2 spins, 4C, 1. You must get only 4 lines. But how I got 1 line? What I in that formula I didn't say the strongly coupled or weakly coupled. General formula, when 2 spins are coupled, you must get 2nC n minus 1 transitions. That turns out to be 4 lines. But why I got only 1 line in the A2? Remember, still what happens was in the A2 case, two central lines will coalesce, will give a single peak, but two outer lines will disappear. Right? How does it mean? What does it mean? Why you are not getting four peaks? That is because in the A2 case, what happens is, when we go ahead further, I'll show you. It so happens there will be three symmetric transitions, symmetric energy levels. One is antisymmetric. Symmetric to antisymmetric transitions are forbidden. As a consequence, you will not see four peaks. You will see only two peaks of equal intensity in the case of A2. So that's why A2 systems always give single peak. And single peak is nothing but two peaks overlap and outer peaks are not visible at all. And you can smoothly go from AX to AB and A to A2. Start with AB, you can keep on increasing the field, take it to AX. Start with AB, take it to AX. Start with AB, keep on reducing the chemical separation, make them equivalent, you can bring it to A2. Is a continuous transition. Transition to AB to AX is continuous and AB to A2 is also continuous. So this is what you please remember.